Hello, welcome back. In this segment, I will talk about the division algorithm, which is one of the fundamental theorems in number theory. Although I call it division algorithm, it is more of a theorem rather than algorithm, but the proof has the idea for how to construct a division algorithm. Okay, so let me give you an example first before I talk about the general theorem. If you take numbers, say 15 and 6, right? 15 can be represented as 2 times 6 plus 3. And if you take any number like -10 and 6, plus and minus 10 as minus 2 times 6 plus 2. If you're given two numbers A and B, there exist unique numbers Q and R such that A is equal to Q times B plus R. That is the basic definition of the division algorithm. We need this elementary idea for many segments. And what you are also seeing is that basically if you divide A by B, you get a quotient Q, and you probably will get also remainder R. So the quotient, the remainder are all connected in this nice expression, A equal to Q times B plus R. You're basically taking A and dividing it by B, you get Q as a quotient, R as a remainder. And one more thing is that R itself is, another important thing is R is less than B, okay? R lies between 0, inclusive of 0, but less than B. All right, so how do we prove this? For any two numbers A and B, we need to show there exists unique integers Q and R. So I'm going to first drop the word unique. I'll first prove that from A and B, we can construct Q and R. Okay, let's consider a visual representation. Okay, for simplicity, I'm going to assume A and B both are greater than 0, just for visualization purpose to start with. Okay, so let's assume we have a number line. It's not a perfect line, but it's a number line. And here is your 0, right? Let us assume here is your B somewhere, and somewhere here is your A. Okay, so what we are going to do, we'll keep on going to subtract A by B. Okay, so this will be A minus B, and this will be A minus 2B, and so on. Keep on subtracting it until we get the smallest number here. Okay, meaning somewhere here, let's say over here, I get A minus, we don't know Q, but I will show you this algorithm in a moment. Okay, so this number, we call it R because it's same as A minus QB. That's what we are going to find out. All right, so what we are going to do is basically construct a set S, right? Made of numbers as follows. We have A, on the right hand side, we add B, so it will be A plus B, A plus 2B, and so on. On the left hand side, we keep subtracting B. Okay, so we have this infinite set. But the first point I wanted to climb here is that this infinite set must contain a number, at least one number must be greater than or equal to 0. Okay, how do we confirm that? Let us assume for a moment A is greater than or equal to 0. If that's true, obviously we have A here. So our claim is correct. There is a which is non-negative. What if our A is less than 0? Okay. In that case, it's easy. If A is less than 0, since we are taking A and keep on subtracting B to the left-hand side, what can we say about A minus AB? A minus AB must be one of the elements of the set, right? Because remember the structure of the set is keep A and subtract B, and so on. That means you'll eventually subtract A by A minus AB. Okay, so what can you say about A minus AB when A is less than 0? We can take minus A common. What can you say about minus A? Minus A must be greater than 0, right? Because A is less than 0. That means this part is greater than 0. And this part is also greater than 0 because we assumed B is greater than 0. Okay, so this means A minus AB is greater than 0 as well. Okay, so we found out that A minus AB is greater than 0. All right. Okay, well, one more thing. B can be 1, right? That means I should put greater than or equal to 0. So we do have a non-negative number in any case. Either A is less than 0 or A is greater than or equal to 0. We find a non-negative number in the set. So this is an interesting observation. Now, what we are going to do, we are going to select among this set of all non-negative numbers in There could be negative numbers also in the set, but we are only now focusing on the non-negative numbers. Let's select the smallest number in that set. Any set of non-negative numbers, there must be a smallest set. That's a property of integers. So we select a smallest number. Let's say such a smallest number is of the form a minus qb, right? That must exist in the set because that's how the set is constructed. And we call that R, okay? So what we need to prove now is, we need to prove R is less than B. So what happens if R is greater than B? If R is greater than B, what can you say about R minus B? R minus B is A minus Q plus 1B, right? I'm just taking a B common. Okay, but then we also know that R minus B is smaller than R, because from R you're getting rid of B. That means R minus B must be smaller than R. So what we found out is another number smaller than R, okay? But that's a contradiction. I claim that R is less than B, right? That's the claim. R has to be less than B. What happens if R is greater than B? If R is greater than B, what can you say about R minus B? R minus B is of the form A minus Q plus 1B. Okay, but this is greater than 0 or greater than or equal to 0. Why do you say that? Because we assumed R is greater than or equal to B. If R is greater than or equal to B, R minus B is greater than or equal to 0. Okay, which is a problem because we found out another number, this number, right? Which is smaller than R, of course, because we got this by subtracting B. So we found another number in the set which is smaller than the number that we thought is the smallest one. That means R must be less than B. Okay. So what we have found out is that A minus QB is the one that we are looking for, and we find out in the set yes. Okay. So the problem of finding Q and R is solved. Next part is to prove that the numbers Q and R are unique. How do we prove that part? To prove the numbers are unique, I'm going to make use of this assumption that, well, we already proved that assumption. A is equal to QB plus R, right? So what happens if there are two numbers like that? Let's say A is equal to Q1B plus R1, and A is also equal to Q2B R2. Okay. I'm going to prove Q1 is equal to Q2, R1 is equal to R2. So how am I going to do that? We do know that R1 is less than B. We proved that earlier. And similarly, we have to assume R2 is also less than B. Okay. Okay, well, because of this assumption, what can we say about this? It means this implies R2 minus R1 is also less than B, right? If R2 is less than B and you get rid of something, you will get an answer which is smaller than B. Okay, just from this constraint, we get this. Okay. Let us assume one more thing now, that R1 is smaller than R2. What happens if R1 and R2 are not equal? In that case, let's subtract these two. So we get and reorganize it. So we get 0 is equal to Q2 minus Q1B, right? Plus R2 minus R1 plus R2 minus R1. Okay, I'm going to reorganize this a little bit further. This is the same as saying Q1 minus Q2. We just took the common minus out and then moved to the left hand side. Therefore, Q1 minus Q2B is equal to R2 minus R1. Okay, B divides R2 minus R1, right? Because we wrote R2 minus R1 as a product of B times something. So what can we now say when B divides R2 minus R1? It means this implies B is less than or equal to R2 minus R1. But that's a contradiction because we already proved that R2 minus R1 is less than B, but here we say B is less than R2 minus R1 or equal to R2 minus R1. Okay, therefore, our assumption is wrong. Therefore, R1 cannot be less than R2. So this is wrong. That means R1 has to be equal to R2. Okay, so we proved R1 and R2 are equal. If R1 and R2 are equal, now we can easily prove that Q1 and Q2 are equal. Okay, let me quickly do that as well. Since R1 and R2 are equal, what can I do? I can just take A equal to Q1B plus R, because R1 and R2 are equal, let me call it R. And A is equal to Q2B R. So I'm going to subtract both sides. So I get Q1 minus Q2 times B equal to 0, right? But we assumed that B is non-zero. That means Q1 must be equal to Q2. Okay. This implies Q1 must be equal to Q2. So we found out that the quotients are also equal. Q1 must be equal to Q2. We first proved R1 equal to R2. So that means we have achieved the uniqueness claim as well here.